All right. So last thing we did in our previous lecture was so-called linearization. So one thing that we know really well is we know how to fit a straight line, okay, through the data. That's one of the simplest problems. I'm looking for two parameters, A0, A1. And we went through the procedure of trying to minimize the square of residuals between measured data and this model, which in this case is a simple linear model. And since this is a quadratic relationship, it's going to have a minimum, and we can look for that minimum. And minimum is equivalent for looking for where these partial derivatives of this SR are equal to 0. That gives me, in this particular case, two equations and two unknowns, regardless of how much data I have. Okay? And I can solve that using data xi, yi, using these two formulas. And we have implemented that. Now, some equations are, some data might actually require some sort of fitting that is not linear, or linear is simply not a good approximation to the data. And we can actually linearize them. So one simple, if I have any kind of power relationship, again, we're looking for two parameters here. If I went through the procedure of minimizing these residuals, this model would be nonlinear. Derivatives of it would be nonlinear. So I would get like two nonlinear equations in A0, A1, or AB, however I call my parameters. And that's not necessarily so easy to solve. There is a Newton-Raphson variant for systems, but it's not as easy. But I can also take a look at this and just do some transformation of it, literally a little bit of algebra, and essentially do a natural log of both sides, in this particular case, and recognize that basically my natural log of my y's and x in this particular case are linearly related. So I can fit that linearly and then just do required transformation to figure out these two parameters. The actual model is still y is equal to a times e to the bx. Right? And I can do that if I have any type of power relationship. I'm typically not going to take a natural log. It could be in any other way. It's typically some algebra to figure out what transformation of the original data I need to do. And this is a table that gives some most common ones. Now, we have actually gone through the exercise, and we did fit. So here is an example of fitting a linear, that's that same data. This is the linear fit. And this is the power law fit. This one, whoops, over here. Okay? And I can actually compute for linear regression. I can compute this. This is adding one line to that code in linear regression to see the goodness of the fit. This R square value typically we refer to as the goodness of the fit. And you can program this, and if you got here, it's obviously visually that this is the red line is way better fit than the black line. But I can also get that R square for black line is much less than R square for red line. Close to 1 is always good. So between above 0.9 is always good.
And do not go below 0.7.
I wouldn't, right? That doesn't mean that you will not. If that's the only thing you got, that's the only thing you got. Like sometimes you have data that is simply like, if I had a cloud of points literally going around this, right? That cloud of points is not correlated, period, actually, right? But I might still benefit for striking a thread, this trend line through the middle, and still use that, because no matter what curve I go through that data, it's not going to work. So I might still use linear regression, but use it cautiously, understanding that you're missing something in that data description, and the data is depending on two variables, not on just one. And that's the part you're missing when you get like a large cloud of data. Okay? But that's something else that you're missing. You might not be able to measure. So you do what you have to do, but understand that it's not a good description of the data. Yeah. Now, what if we wanted to do something else? So let's say that I had the data like on this line, obviously linear. However, I slice through and with a line through that data, that's not going to look good. Something like parabolic, I'm already cooking. So in that case, my model is a second order polynomial, and I can go through the same motion. So this is my data. This is minus model function of x data, right? X for the data. So then I would take the residuals and square them again and sum them up. So how am I going to get my equations for A0, A1, and A2? The same procedure as for linear regression. Same as what you do on that piece of paper. Where is my minimum for any function? Derivative. In this case, partial derivatives, because this is function in A0, A1, A2. Remember, you know all of the xi's. Maybe there's 5,000 of them, but you know them. Okay? And you know all of the yi's. Maybe there is 5,000 of them, but you know them. So these are known. What's not known is A0, A1, A2, and you're looking for A0, A1, A2 that minimize this. And those A0, A1, A2 partial derivatives of SR with respect to A0, A1, A2 have to be 0 at that point to get the minimum. Okay? And again, this is a quadratic relationship in A0, A1, A2. So quadratic functions that are positive in their values, they're going to have a minimum, a bottom of the bowl. Right? They're not going to have a maximum. So we just go through the same procedure. I take a partial derivative of this. Okay? And this is something that I have asked previously on final exams. So go through partial derivative of SR with respect to A0. If I'm doing a derivative of quadratic function, it's 2 times this. The sum doesn't really bother me. I just still keep it there. And then times derivative of this, whatever is inside these brackets, with respect to A0, which is -1 in this case. So that's basically written down here. That has to be 0. Then I do a partial derivative with respect to A1. So it's -2, and then times this, times partial derivative with respect to A1, which is minus xi, and that's minus xi. Yes? That has to be equal to 0. Sums have to be there. I do that for every element of the sum. And then partial derivative with respect to SR with respect to this should be A2, I apologize. Partial derivative with respect to A2 should be, so this is my A2 term, so it's minus xi squared. Xi squared, again, is just a number. Okay, it's not a variable. So when I clean that up, I have a linear equation in A0, A1, A2 in first line, same in the second line, even if it looks a little ugly, and same in the third line. And when I take them out, so it's actually, I get n times, because I have sum of 1 n times A0, plus sum of all of the xi's A1, plus sum of all of xi squared is A2, is equal to sum of yi's. Because sum of yi's basically goes to the right-hand side because it's not multiplied by A0, A1, or A2, which are my unknowns. Clean up the second one, clean up the third one. So even if the algebra here takes a little bit of writing, do you understand how I got from there to there? This was on final last year. Okay? just to derive that. I could give you anything here, as long as I give you a model, that model has certain number of parameters. Take partial derivatives with respect to those parameters. Clean it up. And then this is a linear system. If I gave you data, x and y, and say fit a parabolic function to it, how would you program that function? With data xi, you have xi, yi for all of the i's. Let's two vectors, xi and yi. So this, you would just set up this linear system. It's a 3 by 3 system. You define a matrix A. This is the element 0, 0, element 0, 1, the sum. We already created those sums. This one, right? So just compute all of these sums and put them in a matrix and create your sum for right-hand side. Not difficult, just a bunch of typing. And then you solve the system, and the vector solution has 3 elements. First one is your A0, second one is your A1, and third one is A2. Yeah? Again, we can do this in any way, so this would be an example fit for a parabola. Now, what if I had dependence of 2 variables? So my y depends on x1 and x2. In the simplest case, I would try to strike a plane through that. So I create a model. My model, this is a simple plane. You're used to calling this z, x, y, whatever you call it, right? This is a function that describes the plane. And then there's some error. And again, I would minimize the residual between my actual data and my model. And I'm again looking for these parameters through partial derivatives. It's 11:50, so my calendar is warning me that at noon I have office hours. So at noon I have office hours.
Can you post previous finals so we have something
I
to study?
don't typically release final questions, but I do comment on what they should be. So I just told you what one of them was. And that's a matter of practice. I will give some practice problems, but I will not release final.
That's mainly what I was.
Yeah.
Yeah.
Oh, you go ahead. I was going to ask about the extra credit for Cockroach pairs.
Yes, I didn't put that in.
So
I will.
I didn't want to rush you, but I just
Oh,
wanted
no.
to make sure
I need to
didn't
do
miss
that.
it.
So
Okay.
be sure to
As long as
remind me
you're doing
again
it.
if you don't see it, okay?
Thank you.
I got it all. It's in my email.
Okay. So tomorrow we meet at 2 o'clock.
Or 126.
And so it's going to be like the same, like.
I'm going to give you 2 questions.
So 2 questions.
And basically, I'm just going to add up.
So what's the
current
max?
score.
Like what's the max point you're getting?
40. So you can add that much to your exam.
Okay. And it's gonna go over like the same stuff. It's not gonna be anything new, right?
Yeah, it's going to be 2 questions, probably like those problems 3, 4, or 5, something like that.